It's a little after 3. I was going to have the class vote, so I was waiting for a couple more people to trickle in. But you guys hold a lot of power, I guess. Maybe I'll just go through some announcements first. So what's going on? This is the last week before Thanksgiving break, unless I've mixed something up. That's correct, right? And so your homework's due on Thursday. Is that also right? OK.
Tuesday, not this Thursday.
Tuesday after Thanksgiving.
No, next Tuesday.
So next Tuesday we have class, and then Thanksgiving.
Yeah.
OK. All right. That's why Barnabas and Adon are there. OK. So your homework's due next Tuesday, apparently a week from today. We've graded your midterms, and we already talked about them. And Adana is going to have them to hand back to you after class today. And if you don't get them after class today, you can go to recitation tomorrow. She'll also
to my office hours.
have them there. Yeah. Oh, and we have one more kind of thing we decided to do with the midterm, which is that so up until a week before the little test, so I can't remember what day that is. The little test is December 3rd. So a week before that would be Tuesday, November 26th. A week before the little test. And I'll send an email out about this to make it more precise. You can take your midterm. You can actually correct it. So you can go through and on the back side of each page, go ahead and correct any mistakes that you made and hand it back in. And you'll get a maximum of 2 points back for that. It's not a lot of points, but it's something. And I think it's good practice for the little test to go through and correct your mistakes. And then you'll get pretty easy couple points back on the midterm. So I would definitely recommend that you do that just as a study guide. And then just turn it in, and we'll give you some points for that. And then you can get it back in time to study for the little test. All right. So now I'm going to do something pretty unorthodox. The slides for this lecture are up on the web. So you can look at them regardless of what we end up doing in class. But last Thursday, if you guys remember, the projector ran out, so I did the whole class on the blackboard. And so it seemed, based on a few of the responses on the feedback form, that people actually liked that. So I was going to hold a poll right now to see whether or not people want to see the lecture on the blackboard today or via slides. So just like a word of warning, if we do blackboard, we're not going to get through as much material. So this lecture covers coordinate descent. It also covers a bit of graphical model stuff at the end. But the lecture is mainly on coordinate descent. If we do blackboard, I don't think we'll get to much of the details of the graphical models or the graphical lasso stuff at the end. But blackboard has its advantages too. So how many people want to see the class on slides? Raise your hand. And raise them high, because this is going to change what happens the next hour and 20 minutes. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. OK, how many people want to see on Blackboard? Oh, unfortunately, not a majority. Yeah. Well, in keeping with democracy, I guess we're going to go with the slides today. So sorry to you guys that want to see it on the Blackboard. But I'll try to be concrete on the paper here so we can at least see some things written down. OK, so today's lecture is on coordinate descent. Some people call this coordinate-wise minimization. I'd say most people call it coordinate descent. It's probably more accurately described as coordinate-wise minimization. But just because it's the tradition and it's what it's called in the literature, we're going to call it coordinate descent. So far we've seen some pretty sophisticated methods. We've talked about first-order methods, second-order methods, quasi-Newton methods, interior point methods, and then dual methods last time. Right, and some of those got pretty sophisticated. Today we're going to talk about a really simple algorithm. It's about as simple as you can get conceptually, at least. And it's surprisingly efficient and scalable in a lot of cases. Okay, and so the focus is going to be on coordinate descent, or like I said, more accurately described as coordinate-wise minimization. So we're going to start off with a sequence of questions to try to develop some intuition about whether this kind of thing is even going to work in the first place. So here's the question. if I give you a convex differentiable function f, okay, and I tell you that I have this point x such that along each component I've minimized f. In other words, if I take a step, or if I'm at x and I take a step in the direction x plus, say, delta times ei, which means that I try to move along the ith component by any amount delta, if doing this means that I only make the function bigger than it was at x for all delta and all I. Right, so this is just the ith standard basis vector. So this guy is all zeros, and it's just a 1 in the ith spot. So the question is, does this imply that x is a minimizer of f? Okay, so how many people think this is true? That if I have a convex differentiable function, I have this point that I can't move in any of the along any coordinate axis to make the function smaller, then at that point I've actually minimized f. Let's get a raise of hands for those who think this is a true property. Okay, how many people think it's false? Okay, a couple people kind of doing this with their hand or something. Okay, so this one's true. The proof's pretty simple, but the picture actually helps to look at. Right, so here's a differentiable function, convex. Suppose I'm at the bottom. Right, clearly I can't move along x1 or x2 among any amount because that makes the function bigger. And in fact, if I was anywhere else than at the bottom, I could just take some step along one of the coordinate axes and make the function smaller. Okay, so what's the proof? Well, if this property is true, it means that the ith component of the gradient is 0. Right? Because I can think about the function as being restricted to just along one component direction. So this is saying the partial derivative with respect to, say, xi is 0. That's what this thing is saying. And so if I know this is 0 for all I, that's like saying the entire gradient vector is 0. Right? Because it's just the collection of partial derivatives. So I'm just writing this to mean the partial derivative of f with respect to x1. Right? And we know that for a convex differentiable function, this means we minimized it. Right? So this is good enough to say that x minimizes the function f. All right, so if we ever want to minimize convex smooth functions, we could just consider kind of doing component-wise minimizations, right? Because we know that if we ever reach a point for which we can't move any direction along the components to improve the function, then we're at the minimizer. Same question now, but let's just think about x as being convex. So the question is, so here f was convex and differentiable. And how about if f is just convex? So the question is the same property true? Does yeah, I won't rewrite it, but is this property true? That if I have a component-wise minimizer, is the function minimized? How many people think yes? Okay, so a majority again. How many people think no? Okay, got a couple no's. Why do you think no? Either of you guys, what's the intuition for that? I wouldn't be asking this question otherwise, or?
That was my first guess. But then I feel that if it's just like a V shape, if it's not along the sort of coordinates. I mean, my visualization is not very good, but I think there might be some way to get it that you can't make progress. Like the differentiability might help.
Yeah, your intuition is great. So the answer is no. And so here's a counterexample, and it's kind of like what you're saying, which is this is the function. it's kind of like the front of a boat. Okay, so it's convex, but it's not smooth. It has this ridge on the front. And I have x1 and x2. And actually, if I'm at somewhere along this ridge, then I can't move in any direction x1 or x2 to make the function smaller. Moving in either direction can only make the function bigger. And so to convince you that's true, I actually made a contour plot here. Okay, so that means that I've taken a bunch of slices of this image at different, say, z values, x1, x2, and say, so let's call this axis z. And I've drawn the contours. And so look, if I'm at the point of that contour along the ridge, then if I move in the x2 direction, it only makes the function bigger. And if I move in the x1 direction, it only makes the function bigger. But I'm not at the minimizer. The minimizer is like down there at the bottom of the boat. So I have to move jointly in x1 and x2 to make it smaller. Individual moves won't do it. Okay, so this might kind of give you a sinking feeling that, why are we given this lecture? Because if we can only minimize smooth functions, then it's not very general, right? But there is a saving grace. So the answer was no, just for f convex. Let's suppose that f was the sum of, we have this similar trick, sum of smooth function plus non-smooth function. So g is our smooth guy, and h is our non-smooth guy. But I'm going to make a very kind of specific assumption about h, namely that it's the sum of a bunch of functions of components individually. So h can be written as the sum of hi, xi. So these could be non-smooth. These could be as complicated as we want, as long as they're convex. And each hi is only a function of xi. So we call this part separable, the non-smooth part separable, because it adds up as it's a sum of component-wise functions. Okay, so now you can probably guess the answer, but how many people here think that we can do coordinate descent? That component-wise minimization actually means I've minimized the function? You can raise your hand. Okay, so I'm guessing people know where I'm going here. So the answer is yes. So if we have suppose f of x is g of x, which is smooth, plus the sum of hi of xi. These could be non-smooth, right? But they're both convex. Then actually, in this case, component-wise minimization is good enough to ensure optimality overall. And the proof is very simple. I'll go through it carefully, because this is really kind of the only exercise we'll do this lecture. Okay, so if I know that, let's suppose I know that xi minimizes gx plus the sum of hi xi I'll write this as a function of y so you don't get confused. So let's suppose that xi is the minimizer of this function of y along the ith component, so along yi. I can vary yi however I want. I'll let the other variables yj, j not equal to I, be fixed. And xi is the guy that minimizes this function. And what does that mean? That means that if I take the derivative of this with respect to just yi, or actually, in this case, a subgradient with respect to yi, then it has to contain 0. Right? That was our subgradient optimality characterization of any function. Okay, so let's think of this guy as a function of just yi. Take a subgradient with respect to yi. What do we get? We get the gradient of g in the ith component. This is the ith partial derivative of g with respect to yi, plus I'll write this sum as the sum over j, because we're just considering one I. what's the subgradient of this guy with respect to yi? Of this term. Right. It's just the subgradient of hi of yi. Okay, and actually, what I want to do is stick an x, because x was the minimizer, right? So none of the other terms depended on yi, so that they didn't appear here. Right, so we know that this has to 0 has to be in the subgradient. That's subgradient optimality. Okay, so what does that mean? It means that the negative ith partial derivative of g at x is in the subgradient of hi evaluated at xi. And now let's just write out what this means in terms of the definition of subgradients. So if h has this as a subgradient at xi, it means that for any yi, if I look at h, then it's bigger than or equal to hi at xi, right, plus the subgradient transpose yi minus xi. And the subgradient I know is, or a subgradient is minus the ith partial derivative of g at x. So minus this transpose yi minus xi. This is true for any y. Okay, in other words, I'm just going to rearrange this to say that I'll put all the terms on this side, which means that the ith partial derivative of g evaluated at x transpose yi minus xi plus hi of yi minus hi of xi is bigger than or equal to 0. Again, this is true for any yi. Okay, so just very, very simple steps here. We just looked at the subgradients, concluded that it had to contain 0 at x, and then I just used the definition of a subgradient right here. I've just plugged in this for a subgradient in the definition, and I've gotten that the ith partial derivative of g transpose yi minus xi plus the difference in the h's between yi and xi has to be non-negative for any yi, provided that xi minimizes that function along the ith component. Okay, but actually this is it. We've proved the result now after just that couple lines, because let's look at the whole function f of y minus f of x. And we know this is true for any I, because along any I we've minimized it component-wise, say at x. Then this is the, it's going to be g of y minus g of x plus the sum of hi yi minus hi xi, I equals 1 to n. Okay, and now we almost have the result. Can anybody see what we need to do to get the result? There's one step we're missing. Right, we'll just use the convexity of g. Right, so the first order condition is that this difference has to be bigger than or equal to the gradient of g. Oh, so just so I don't confuse you, by the way, sorry about that. There shouldn't be a transpose here. This was just a number. This was a univariate case. So there is no transpose. The subgradient here is just a number. Here we have, right, the first order definition for convexity is that this is bigger than or equal to the gradient of g at x times transpose y minus x plus the sum of hi yi minus hi xi. And now I'm just going to collect terms. right, this is just the sum of the products of the components, and that's just this. Gix times yi minus xi plus, I'll just add this term into the inside of the sum. Right, all I've done is collect terms. And then we proved just up here exactly that this was positive. So the whole thing is positive, which means that for any y, f of y is bigger than or equal to f of x. OK, so that was a proof of the fact that if we have a convex function that's the sum of a smooth function, any smooth function, plus any separable function, that component-wise minimization is good enough to ensure optimality overall. And so a picture is not a proof, but here's a picture, basically, of what the difference is between this case and this one. If I have a non-smooth function that's a sum of component functions, then all of the non-smoothness has to occur kind of only within any one component direction. It can't happen across component directions. So if I'm actually minimizing across component directions, then I can kind of overcome these non-smooth kinks in the function. Whereas in this case, right, the function was non-smooth along the 45-degree line. Right, so minimizing along xi or x1 and x2 wasn't good enough. OK, so this fact that we disproved, it suggests a very kind of natural and, in a way, kind of obvious algorithm for minimizing these smooth plus separable functions. We'll just use what's called coordinate descent. And like I said, a better description is coordinate-wise minimization, but keep in mind that we'll use kind of both terms, where we just start with a point, and then we just repeatedly make component-wise full minimizations. So I start with some point x0, and then along the first component, I just minimize that function, fixing all other components in the first one at whatever value they had at x0, and then doing a full minimization over the first component to get, say, x superscript 1 in the first component. And after I've done that, I move to the second component, and I fix all their components but the second component, and I minimize fully to get the new second component, and so on and so forth. And then when I get to the end, I just cycle back over to the first. So I repeat these cycles of minimizing over each component individually. And I know that when I get to a point where my updates don't change, then I have the global solution. Right? We've proved that at any point, any fixed point in this algorithm where it actually doesn't change because you're at the minimizer component-wise, you know that you're at the global solution. OK, so one thing to point out, it's actually very important that after you solve, say, the first step, that in the second step you use the updated value of x1, not the old value. Right? So it's very important that here, in the kth iteration, after I've found x1k, I plug in x1k to the function when I'm going to minimize over x2. I don't use x1 at from iteration k minus 1. I'm always using the most updated values of the parameters. That's very important. And so we'll return to that point in a second. So there's this pretty recent work, although I think Paul Sang had lots of papers earlier than this, but the paper that everybody kind of quotes as the seminal work on coordinate descent was from 2001, that proves that if I have some function f that's has very weak conditions, it's just basically continuous on one of its sublevel sets, and it attains its minimum, then any limit point of this process is going to be a minimizer of coordinate descent. So this process, any minimizer of this process is going to be, any limit point of this process is going to be a minimizer of coordinate descent. So if I do this process and I encounter some x that I revisit all the time, then it's going to be the minimizer of f. And I don't think this stuff is terribly important to be super detailed about, but if we use a couple reanalysis facts, it tells us basically that we're going to have a subsequence converging to x star because it's a bounded sequence. And we'll always get convergence in the function values because of monotone convergence. Okay, so the thing to remember, though, is that there will at least be a subsequence of these coordinate descent steps that converges to the minimizer. Okay, so if you're doing this and you repeatedly visit the same point over and over again, then that thing is a minimizer of f. So here are some important notes. The order of cycling through the coordinates is arbitrary. So at any iteration of coordinate descent, I can choose a permutation, and I can visit them in any order. It doesn't have to be 1 through n. It can be just a permutation of that. And I can anywhere replace individual coordinates with blocks of coordinates. So instead of minimizing over x1, then x2, then x3, then x4, for example, I can minimize over x1 through x5 jointly, and then x3 through x10 jointly, and x11 through x15 jointly. As long as I make those full joint minimizations, I can do blocks of coordinates, just the same as individual coordinates. Did you have a question?
So we say that summation of the convex function and non-convex function is gx, right? So I was thinking that gx equals c, a constant. It's convex and it's differentiable. So that fails. The definition fails there. Just set it to be a DC level, basically.
Gx is a constant?
Gx DC.
Yeah, well, then any point is a minimizer, right?
Right, but then the definition, the coordinate descent will fail, right? Assuming that like the problem of the bow that you had, like that the function that you had which looks like a bow,
Yeah.
right? Now I add c to it. I move it up or down. It's not going to, the coordinate descent is going to fail anyway, right?
I guess, are you more concerned about this example or about what I said here?
The definition, I'm like saying that we are just putting g is convex and differentiable.
Yeah.
I say gx equals c is convex and differentiable.
Yeah.
But it fails, like coordinate descent won't do anything, right?
This also requires that your h's are separable. I think that's the argument.
I have to say I didn't quite understand the question. Did you want to repeat it so that, or did you?
I just missed the separability.
Okay.
Right.
Okay. Got it. Right. So this was an example where it didn't work. With the separability, it did work. Okay. So here's the most important kind of note to remember, because people make this mistake all the time. And in fact, part of the history of why coordinate descent wasn't used early on was because people didn't pay attention to this. And so they were kind of misled, which is that if you don't make these one-at-a-time updates, meaning you don't solve for x1, then use the new value of x1 when you're solving for x2, then you use the new values of x1 and x2 when you're solving for x3, and so on and so forth. If you just do each component minimization individually without updating, and then at the end update all the components to their new values, and then do it again, then it does not necessarily converge. So that's called the all-at-once strategy. Some people call this the shotgun coordinate descent, and the one-at-a-time is called the shooting method, or shooting coordinate descent. Right, it's the difference between kind of making individual component moves or just doing something all at once. So this method, where you update them individually without paying attention to the previous components in that iteration, does not necessarily converge, like I said. And so if you try that on simple examples, you can see that it quite often will fail. And that's kind of too bad, because it's really this one. It's the all-at-once update scheme that's more amenable to distributed computing, right, or to parallel computing. Because you'd like to really send off things on their own processors and have them do it independent of each other. And so people have worked on trying to amend this for various problems, including, say, the lasso. And so there's nice new work on this. But generically, it fails. Yeah? I mean, usually, if you have H, it should be pretty obvious from its form that it's separable. We'll go through some examples. So you'll see, basically, if you can write H as a sum of any functions of components, then it's separable. And so we'll go through some examples. And sometimes, if H is not separable, then I mean, one common trick we do all the time is derive the dual. And maybe in the dual formulation, we'll get, again, a smooth plus non-smooth where H ends up being separable. And I'll try to make a point of talking about that. It's not on the slides, but there are problems that are kind of mentioned here where that's the case. So let's do a really simple example first, linear regression. Let's suppose we want to minimize the least squares criterion. Right, we don't have to use any algorithm for this. We could just we could solve this directly, right, using linear algebra. But it's kind of instructive to see what happens in this case. So we're going to consider minimizing over the ith component of our optimization variable. Here, that's beta with all the other ones fixed, beta j. So in other words, I can take just the derivative of this guy with respect to beta I, fixing all the rest. And that has to be 0. So I get this expression that 0 is equal to the ith partial derivative of my function, which is xi transpose y minus x beta. Right, the gradient is I guess it's actually negative this, just so I don't confuse you. The gradient is x transpose x beta minus y, so its ith component is just the ith column of x, xi transpose x beta minus y. And I'm going to write that as I'm going to write this as xi beta I plus x minus I beta minus I. So this is just the ith column of x times the ith component of beta I. These are all but the ith column of x. I've just extracted it times all but the ith component of beta. And now remember, I want to solve for beta I here, thinking of all the other guys fixed. So this is just a univariate minimization problem. And I conclude that right, beta I is just xi transpose y minus the fit from all the other betas divided by xi transpose xi. Right, because that was the leading term I had on beta I. And everything's univariate here. I just divided by that. So this is what I do for the ith component. And then I update that value, and I do it for the I plus first component. And then I update that value, and I keep going like that. And cyclically, I repeat these steps. And that's going to give me the least squares solution. All right, so this is a really simple algorithm. You can implement it in your favorite language in no time. And so what we're going to see is it outperforms gradient descent by a pretty large margin. So gradient descent, what does it do? Let's see. This should be a total review for you guys. What are the gradient descent update steps for beta? So beta, I guess we'll do beta plus. The new value of beta is beta, and then what do I do? Minus some step size, t times the gradient, which is right. So it's x transpose. I'll write it as y minus x beta, and then I'll put a plus there to get the two negative signs to cancel. So the forms look different. The forms look similar, at least. Here I'm taking the old value, and I'm adding x transpose the full residual times some constant. Here I'm only using the residual just on all the variables except for beta I. And I'm setting beta I equal to that exactly. And then I'm dividing by xi transpose xi. OK, so kind of face value, these look similar, but they perform very differently. Here's the convergence curves for those. So, oops. So after less than 20 iterations, Courtin descent brings the criterion value down to about 1 to the minus 10 from the optimal criterion value. This is a log scale. And after 50 iterations, gradient descent's somewhere at like 1 to the minus 5, or 1 times 10 to the minus 5. OK, so they're converging at very different rates. And then one thing you might ask is, well, is it really fair to compare one cycle of Courtin descent to one gradient update? Here, k here is one gradient update or one cycle, full cycle for Courtin descent. Because if you look at this, how much work am I doing here? It looks like I'm doing a matrix or a vector-vector multiplication, right? Which is like, this is like going to be, actually to form this even, sorry, right? I have to do a matrix vector multiplication, which is like n times p operations here. And then I have to do another vector-vector multiplication, which is like another p operations. So the whole, this alone is like n times p operations. And then I'm doing p of them, right, because I have p components. So like one cycle of Courtin descent implemented naively is like np squared operations. And what's one gradient update? It's just, you know, the real cost is just evaluating this, say, which is n times p. So maybe naively it looks like Courtin descent takes np squared, gradient takes np, so it's not fair to compare one cycle of Courtin descent to one cycle of gradient descent, or one iteration of gradient descent. But here's where Courtin descent can be really efficient if you are very careful. There's an implementation for Courtin descent here that actually has one entire cycle only taking np operations. I'll go through it really quickly, and then we'll take a break. So what we do is we write down, I'm going to write this update using an arrow, because otherwise the notation may look confusing. Maybe just to be consistent, I'll use the same notation here. So basically, all that requires is for me to realize that this guy, y minus the fit from all but the ith variable, is equal to xi transpose y minus x beta plus xi beta I divided by, again, the same thing, xi transpose xi. And I'm going to call this r. This I'm just going to call r. It's the residual. So it's xi transpose r over xi transpose xi plus I have xi transpose xi and I have xi transpose xi, so they cancel and I just get beta I. So if I knew the residual vector, if I knew y minus x beta, then look, this step is very cheap. It's no longer np. It's just, this is a p vector, that's a p vector. That's just p operations. And this is the old value of beta I, so that's nothing to add that. So if I knew what r was, each step in the cycle only takes p operations. And how do I get r from what I had before? Well, updating r actually only takes n operations from the previous cycle. Because in any cycle, all I've changed is one component. So basically, I have to subtract the old value of xi beta I and add the new value of xi beta I from what it was in the previous iteration. So in each iteration, I update r in n operations. And then I do this, which is p operations. So the total cost there is just, you know, right, it's like p if p is bigger than n. That's it. And I do that n times, so that one entire cycle of Courtin descent is just np operations. So it's really just the same cost as running gradient descent. And this makes a huge difference in practice. And this is what the difference between making Courtin descent fast in practical and impractical if we hadn't seen this trick. OK, let's take a break, and we'll come back to the rest of Courtin descent. OK. So, all right, so we saw that Courtin descent can beat gradient descent, right, by a pretty hefty margin. The next thing is that we're going to see here is that it can actually beat accelerated gradient descent by a pretty large margin as well. So we didn't talk about acceleration in lecture in that much detail, but we mentioned that accelerating gradient descent achieves the optimal rate of convergence for any first-order method. So if you look at any first-order method, you can't do better in terms of the form of the convergence rate than accelerated gradient descent. But from this picture, Courtin descent is still beating it by a large margin. So Nesterov acceleration I'm using here, it's shown in green. And so the catch here is that Courtin descent is not a first-order method. It's using a lot more than first-order information. look at these steps, right? It's actually able to, applying coordinate descent is assuming you're able to solve each one of these component minimizations exactly in a sequential fashion. Right, so here it's able to kind of leverage a lot more information about f than just its gradient. In fact, it's minimizing f along the coordinate axes. Okay, so it can beat the optimal first order method by a large margin. Yeah?
So the least squares problem, you can get an explicit solution, but in general, I assume you can't always find an explicit solution for b sub I, something beta sub I or something, so you have to do like gradient descent on the coordinates to...
Yeah, so that's a good question. So the examples we're going to go through are all examples in which you do have an explicit solution for each one of those individual minimizations, except for the last one. When we talk about the graphical lasso, it'll be a case in which each one of those individual, in that case it's block minimizations, we don't have an explicit form for. Generally speaking, it's not a good idea to use it for problems in which you don't know these individually and you have to run like another subroutine. But that's not always the case. The graphical lasso is a case in which we reduce it to a bunch of problems, each one is fairly difficult, and we solve each one of those problems using another method. But it actually, in the end, ends up being worth it. You just have to see depending on the application. If you have a good solver for this, either explicit or approximate but pretty good, it can still be a good idea to use coordinate descent. Yeah, that was a good question. So I'm going to skip through the lasso case because we've seen so much of the lasso, but I just wanted to answer an earlier question, which is how do we know that like our function is separable? We'll take the one norm, for example. Right, I can write that as a sum over all I of the absolute values of beta I. Right, so the individual component functions are here, just absolute value functions, so this is indeed separable. How about the 2 norm squared? Right, that just looks like this. Again, that's indeed separable, but it's also differentiable, so we wouldn't really need to treat it as non-smooth part. How about the 2 norm? Yes or no? Shake your head if you think no. Yeah, it's not. So actually, as written, we could not apply coordinate descent to this problem because it doesn't separate as a sum of, component-wise functions. Okay, in the lasso case, it's really very similar to the linear regression case. We just take this expression that we got for what we would have before, and we soft threshold it. So it's just as efficient as linear regression. All we add is an extra one check. Is this number bigger than this value? Is it smaller than minus this value? Or is it in between minus and positive this value? So it's just as efficient. Nothing changes in terms of the computational complexity. And it's also very, very fast for the lasso. Well, I guess we'll return to that in a second. But I'll go through box constraint regression a little more carefully because this one's a little bit less, just slightly less standard, I guess. So this is our problem to minimize the least squares loss subject to the infinity norm of beta being less than or equal to some value s. So it's like doing regression under a box constraint. And I can rewrite this, right? Minimizing this over beta is the same thing as minimizing over beta the least squares loss plus the sum of indicators that beta I and the ith component is less than or equal to s. And so this is actually an important representation. I could have also written it as the sum of, as just the indicator that the infinity norm of beta was less than or equal to s, but that wouldn't be separable. This is actually separable. Think of each of these guys as hi of beta I. Right? It's just a function of beta I. And it's not smooth. In fact, it's either 0 or infinity, right? So it's definitely not smooth. But this encodes the same constraint as that one up there. So we could apply coordinate descent to this case. And what would we do? we would just look at basically minimizing over all, say, beta I, considering every other variable fixed. This, which is just a quadratic in beta I, it's a one-dimensional quadratic, just in the ith variable, subject to that variable being in an interval between minus s and s. Okay, so the quadratic, can probably read it off of the slides, but this is going to be like minimizing some quadratic in beta I. A is going to be xi transpose xi over 2. B is going to be xi transpose yi, and C is going to be a bunch of terms involving y and the other x's and the other betas. Subject to, right, just minus s is less than or equal to beta I is less than or equal to s. And so how do we do this? Well, we just plot this quadratic. I mean, not computationally, but intuitively. We're going to put down this quadratic, and we'll write down the interval minus s to s. And if the minimizer happens to be between minus s and s, that's the answer. That minimizes the quadratic. If it's to the right of s, then to minimize this quadratic subject to lying in this interval, we just take s. And if it's to the left of minus s, we just take minus s. That's it. Right, so that's all I'm writing here, just with math notation. That we look at the minimizer of the quadratic, that's this guy, and then I truncate it. If it's bigger than s, I make it s. If it's smaller than minus s, I make it minus s. Otherwise, I leave it alone. Okay, so again, exact same computational complexity as before, because this is just a bunch of checks. And to compute this is just like before. I just use the residual trick. So very, very fast for doing box-constrained regression. How about if I had this problem? Plus lambda times the infinity norm of beta. So in some sense, this is equivalent. Well, I mean, formally, this is equivalent to this problem up here for some value of s and lambda. There's some, right, this is just Lagrange duality. There's some value of s such that solving this problem is the same as solving this problem. It's one is the constrained version, the other one is the penalized version. So how about this problem? Can I do this one by Courtin descent? Is this separable as I wrote it? It's not, right? It's like a maximum. It's the maximum of the absolute value of beta I over all I. So actually, I can't do this with Courtin descent. And so Courtin descent is a method in which it really matters how you cast the problem. Usually, it's no more difficult to solve penalized problems, or in many cases, it's no more difficult to solve penalized problems than constrained problems. But you know, you just can't apply Courtin descent to this problem. I'm not going to cover SVMs because we didn't talk about them in detail this year. We just decided not to do it because most people would have seen SVMs from another course. But I'll just say in a couple sentences that one of the original methods for minimizing SVMs, for finding the solution of the support vector machine problem, was a blockwise Courtin descent, where each block had two variables in it. So this was called SMO, sequential minimum optimization, but it's just Courtin descent done on pairs of variables. And you do it on the dual problem of the SVM. So if you see SVM in another class and you're interested, you could take a look at these slides. Like I said, it's just Courtin descent. The interesting thing is that it doesn't meet the separability assumptions that we wrote down. So this is not a problem in which the criterion is smooth plus separable. So actually, according to the this work we cited earlier and our work that we did in class, we don't know that this converges. So it requires kind of a different treatment to show that this converges. And I don't think people generally use this anymore for SVMs. But at one point, it was like one of the forerunners for solving SVMs. So what's the history of this method in statistics and machine learning? So I'd say generically, Courtin descent's not been given a lot of attention in optimization because it's been so simple. And separable was a class of problems that people in optimization for a long time didn't consider that interesting. But it turns out that a lot of problems in statistics and machine learning do fit this smooth plus separable framework. And this is the history that I know of in the statistics and machine learning communities. Of course, the idea of Courtin descent itself was around much earlier in optimization. But in a master, I think this is Wenjing Fu's master's thesis, there was this paper called the shooting algorithm, which described Courtin descent exactly as he wrote it down. And that was for the lasso problem, for L1 penalized linear regression. And it appeared kind of later again in this paper by Ingrid Debashi and some other statisticians. But it was kind of inexplicably ignored. Like nobody paid attention to it for a long time, for almost 10 years. Even though these algorithms were written and laid out in great detail in the literature, nobody was using them. And part of the reason, I think, was because some people who were quite influential in the field had kind of misinterpreted, right, this very simple point we made, which is if you're not careful and you just update them all at once instead of one at a time, it doesn't actually converge. And so that was, it's kind of funny in hindsight. I think that was the case, that people didn't believe it was worth anything because they're implementing it wrong for a while. And then there were 3 papers in 2007. They were, not like, I don't think any of the authors knew what the other authors were working on it, but they all just kind of appeared in one year, and it sparked this huge amount of interest, and now it's really very commonplace in stats and ML. And there's this one paper, Friedman et al., which really sparked interest, I think, in the communities, because it showed that it can perform just as well as pretty fancy optimization methods, much more complicated for a lot of important problems. So the reasons why you'd use it are there's a number of them. One is that it's very simple and easy to implement. Like I said, you could write Courtin descent for a lot of the problems we talked about easily in your favorite language. A second reason is that if you implement it carefully, which goes beyond just the simple idea of performing component-wise minimizations, but actually pay attention to what information can be shared across steps of each cycle. So like that was the residual vector in the least squares case. Then those can actually attain state-of-the-art performance for a lot of stats and ML problems, or at least competitive with the state-of-the-art performance. And the third reason, I mean, there might be more, but here are 3 that I put down, is that they're pretty scalable in the sense that you don't need to fit all the data in memory. Right? If I'm just operating on one variable at a time, say in linear regression, then I can just pull that one variable from file. And if I have the residual vector stored, then I just keep that in memory as well. I don't have to have the whole X matrix in memory. So here are some examples of where it's used. It's used in the lasso quite frequently. Support vector machines somewhat less frequently. Generalized linear models in the lasso. This was a big extension that I think is quite popular for use now. The group lasso, the fuse lasso, trend filtering, the graphical lasso are 3 other examples where it's used. But for these problems, it's actually the dual problem that you usually apply Courtin descent to. And even regression with non-convex penalties, people use Courtin descent. And so I gave a reference at the end of that. It's a very interesting paper where they actually prove that doing Courtin descent with non-convex penalties converges to local minima that have good properties. So this one is kind of outside of what we talked about in the lecture, but it's still a pretty cool application of Courtin descent. And so what makes it so efficient is the following kind of addition to the generic method, which is that when you apply Courtin descent, warm starts make a huge difference. And so the strategy is usually to solve the statistical problem over a sequence of tuning parameter values, starting with a tuning parameter value in which the problem is really easy and working your way down to one in which the problem is harder. And so just if we think about the lasso, and we have lambda as our tuning parameter value, the pathwise strategy that's employed is to compute the solution at some really large value of lambda, lambda 1, and then compute the solution to some degree of tolerance, and then move to a smaller value of lambda and use a warm start. So use the solution from the first solve as a starting point for the second solve, and work your way down to some smaller tuning parameter value at the end. And beyond that, there's another strategy called the active set strategy that people use, which, again, these two things I think are the reasons why it can be so competitive with more fancy methods, is that in any one of these solves, so to solve any one of these problems, you just make one coordinate pass and you look at the components of the solution, or the iterate at this point, or your estimate for the solution that are non-zero. Call that S. And then you only do coordinate cycles on S. You leave all the other variables alone. You don't even cycle over them. So just one cycle to find which variables have not been, say, soft thresholded in that one coordinate pass. Take those S and iterate on those until convergence. And that'll be really fast because S will be small, right? Especially if these tuning parameter values are large. Once you've converged on that smaller subset of components of beta, you don't know you have the solution because you actually don't know that the other variables are truly zero at the solution. Right? You just did one pass and thought it's probably a good idea to call them zero. So you go back and you make another pass and you check the KKT conditions. If those are satisfied, you have the solution. If they're not satisfied, if any particular variable has the property that xi transpose y minus x beta is outside of the interval minus lambda or lambda, that's the KKT condition, you put it back into S and you reiterate until convergence. So that's called the active set strategy. I kind of went through it fast, but the idea is use the sparsity of the problem algorithmically to speed up computation. And so putting these two things together makes it quite a competitive method. And the first one is so important that in most software implementations of coordinate descent, the one that's kind of the most widely used is called GLMNet, which is available in MATLAB or R. If you ask for the solution at just one value of lambda, it'll actually solve a sequence of about 100 problems just to get there. It'll start with lambda very large, and it'll decrease all the way down to lambda, because that'll actually be more efficient than just doing coordinate descent directly at that value of lambda. And it's because for a large value of lambda, there are very few variables that are non-zero at the solution, so it can use that active set strategy to its advantage. And then as it moves to a slightly smaller value of lambda, it has a really good initial guess for the solution, so it's in a good position. If you just start at some smaller value of lambda, kind of outright from a cold start, then you might have to find a lot of variables right, without much prior information about where the solution might lie in the space. All right, so yeah, so you can check out that package for the. This does any generalized linear model and any combination of L1 penalty with L2 penalty can be done by this package GLMNet. And so it's kind of interesting to note that it's really the sparsity of the problem that in part makes this so quick. So if you were trying to do ridge regression, say with coordinate descent, where the penalty was, whatever this guy wrote down up here, it's the 2 norm squared, then actually this is slower than solving the lasso with coordinate descent because there aren't components of the solution that are zero. So you have to keep track of all p of them at all times. Whereas with the lasso implementation, you can throw out a large part and just cycle over a smaller subset. So how about convergence rates? There's really not much that's been done so far in terms of analyzing convergence rates for coordinate descent. Here's one paper that's from this year that gives a rate for problems of this form. So it's a very special form, right? It's just considering the L1 norm as the non-smooth separable part, and G is some convex function that's differentiable. Beyond that, we have to also assume that some kind of a bit wacky assumptions that the authors of this paper kind of admit that these assumptions aren't very transparent. So besides G being convex and having a Lipschitz gradient, we have to assume that the identity matrix minus the gradient over L is a monotone map. So when we apply that to some vector x, that map some vector x, it only increases component-wise the value of its output, right? So this in the ith component is bigger than or equal to the ith component of the input for all I. So that's a little bit pretty strange as an assumption. And look, this is going to depend on x, right? Because for the capital X, the variables in linear regression, because thinking about linear regression, this would be g of beta. And remember, the gradient would be x transpose y minus x beta. So whether or not this is true might depend on the variables you have in your regression. And there's another assumption, kind of equally strange, which has to do with monotonicity of the gradient and the soft thresholding operator. Okay, so it's unclear when these two will hold. So this is a sign that work in this area, analyzing the coordinate descent rates, is still ongoing. But given these assumptions, if you're willing to buy them for now, you can show that if I do gradient descent, which are the y's, and I do coordinate descent, which are the x's, then at every iteration, coordinate descent is closer to the true function value than gradient descent. It's no farther than gradient descent, and so in particular, it inherits the convergence rate of gradient descent. This is not that strong a convergence rate. It's just what we get for gradient descent, but at least it's something. And what people observe empirically a lot of times is that we get pictures like the one you saw earlier, which is that it really does better than first-order methods. So that's still a pretty open problem, and like I said, there's ongoing work. Okay, so the last thing I wanted to talk about was an application of coordinate descent that was a nice one, and also had to do with blocks of coordinates rather than individual coordinates. And it's another one that's in common use, and it's to solve the graphical lasso, which is a problem when you do graphical modeling. So a very brief review of some of the setup here. Let's suppose we have this data matrix X, and we don't have Y here. We're just in a setting where we just observe features X. And the rows of X, so we'll call those little x1 to little xn, they're independent draws from some normal distribution with mean 0 and covariance matrix sigma. So the goal here is really to describe the components of sigma, which is telling you the covariance between your features. And if we know that we have a multivariate normal vector, z, which has mean 0 and covariance matrix sigma, provided that z is normal, there's this very helpful relationship in interpreting the entries of the inverse covariance matrix, which is that if I look at the ith, jth entry of the inverse covariance matrix, that's 0 if and only if variables zi and variables zj are conditionally independent given the rest. So entries of the inverse covariance matrix that are 0 tell you which variables are conditionally independent. Entries of the covariance matrix itself tell you independence, right? Marginal or unconditional. But the inverse covariance matrix in a multivariate normal model tells you about conditional independence. So that's just a tiny bit of background, but about why you might want to estimate sigma inverse, because if you estimate sigma inverse in this model, it tells you about conditional independence. And so if we want to claim that a lot of variables from our sample are conditionally independent, then we want a sparse estimate of sigma inverse. And one way to do that is to solve what people call the graphical lasso problem, right? Because it just has the L1 penalty. That's where the term lasso comes from, where you take the I'm going to write down the log likelihood for the model, where I've written now sigma inverse as this matrix theta, and S as the sample covariance matrix. And if I were doing this, this would be maximum likelihood, because it's minimized the negative log likelihood. But I'm putting the L1 penalty there, so it's telling me that I want to have an estimate theta of sigma inverse whose entries are sparse and that has a low value of the log likelihood or a high value of the likelihood. Okay, so theta is my optimization variable. It's a p by p symmetric positive definite matrix. And these terms, like I said, come from maximum likelihood. And once I solve this problem, my theta hat is an estimate for sigma inverse. And if I look at the entries of theta hat, it'll tell me something about the conditional independence, believed conditional independence between the variables. So some examples, people have looked at this, and there's numerous examples. I just picked two. This was a cell signaling network, so people were looking at different cells and essentially a biological network of how these various cells respond to different stimuli, and trying to draw arrows to, the lack of an edge here in this graph denotes conditional independence of those two cells. And this was another example of the graphical lasso. This was actually a simulation in which they were showing that if the true graph is this kind of hub graph, then the graphical lasso can often do very well at recovering its structure. So this is this should be something you should try to look at after you learn a little bit about matrix derivatives or matrix differentials. If you take, if I take the derivatives here, really it's the subgradients here, and set them equal to 0, then that tells me, right, that's the first order condition for optimality. That's the subgradient optimality condition. And what's the derivative of minus log determinant? Well, it ends up being minus sigma inverse. The derivative, or the matrix derivative of the trace of S theta ends up being theta. And then I just look at this L1 norm component-wise. So this gamma is just a matrix whose ijth component is just the subgradient of the absolute value of theta ij. So these are the KKT conditions for the graphical lasso problem. If we found a value of theta that satisfies this, then we have the solution. Right? And here, like I said, gamma is just, it's a matrix whose elements are the subgradients of the entries of the absolute entries of theta. And here's where the graphical lasso algorithm is born, just by looking at these, the KKT conditions. And so we write this as, we're going to replace W by, or theta inverse by W. And we're going to realize that at the solution, in order for theta to be positive definite, right, that was part of the constraint region, it has to be positive on its diagonal. And that means that Wii is going to be Sii plus lambda. Right? Just put that to the other side, minus theta inverse to the other side. I get W equals S plus lambda gamma. And in the ith component, gamma has to be 1. And in the ith component, gamma has to be 1 because it has to be the sign of theta ii, which has to be positive at the solution. So we know the diagonal elements exactly of W. W is the optimization variable. And now we're just going to solve for the off-diagonal elements. And we're going to partition each of these matrices into block form. We're going to take essentially a p minus 1 by p minus 1 block of W, a p minus 1 by 1 vector. This is the last column of W except for the last component. This is just a real number, and this is a 1 by p minus 1 row. And we're going to partition all of them. And the coordinate strategy here is actually going to solve for an entire block, that column, W1, 2 at a time. It's not going to go element-wise. It's going to go for an entire block because it knows W2, 2. It knows all of the diagonal elements. We know that ahead of time, right? Because I just said they were Sii plus lambda. So we're going to solve for W1, 2. Then we're going to pop that into W2, 1 because it's the transpose of each other. And then we're going to swap out another column. We'll just, we'll partition it differently. We'll take out another column, put W1, 2 into that big block, take out another column, solve for that column. And we'll go through solving these columns of W cyclically. And as we do that, we're going to solve for theta along the way, because what we really want is theta, right, which was sigma inverse. We don't want to have to invert W at the end to get theta. So along the way, we're going to keep track of theta. And so we're pretty much out of time, so I don't have time to go through the details of the algorithm. But the punchline is that solving each block, so solving for W1, 2 in each block, actually looks like a lasso problem. It's this problem up here. It turns into this problem: minimize beta transpose a matrix beta plus some linear function of beta, just constant transpose beta, plus an L1 norm. And that itself is a lasso problem. So this is a case in which I've reduced a big problem to a sequence of smaller problems. But each of those smaller problems are not easy. I can't do it in closed form. So what you can do is you can apply proximal gradient descent here. You can apply another coordinate descent within here, whatever you want to solve this lasso problem. And then you cyclically rotate through and solve each column at a time. And like I said, this is actually a case in which we're solving for blocks of W which aren't blocks of theta. It's blocks of the inverse of theta. And so it's not quite coordinate descent in the sense that we're not solving for blocks of the optimization variable, but it is precisely doing coordinate descent on the dual of the graphical lasso problem. And so that was a whirlwind tour of the graphical lasso. Take a look at this last slide if you're interested. Another kind of fact about graphical modeling. That was it. We're out of time. I put a ton of references here for coordinate descent just because it's not a method that's usually taught in optimization courses, so there's not like a good textbook coverage of it. But you can take a look at a lot of these references. It'll give you some idea of what's going on in the literature. See you next week. Or on Thursday, rather. Sorry.